In this sequence, we will discuss building blocks to create convolutional neural networks. We will use three different terms: convolutional neural networks, CNNs for short, or ConvNets. These CNNs use multiple different building blocks. Prominently are convolutional layers. There will also be fully connected layers, several nonlinear activations, pooling layers, normalization layers, and so on and so forth. In this lecture, we will discuss convolutional layers, the most important ones, or the ones that give the name, and we'll also discuss pooling layers, and leave the discussion of other layers to lectures in the future. Fully connected layers, or linear layers, we already discussed before. Now, convolutional neural networks really have all sorts of different layers, and the name comes because the convolutional layers are dominant and not because they are almost exclusively used. So in contrast to maybe a fully connected neural network or multi-layer perceptron, people would expect that only linear layers and nonlinear activation functions are used. For CNNs, people typically assume that CNNs are also complemented by other types of layers, such as linear layers. As discussed before, fully connected neural networks conceptually arrange the neurons as vectors or rank 1 tensors. In the example we see here to the left, we can see the input layer that is a three-dimensional vector. The first hidden layer is a four-dimensional vector. The second hidden layer is a four-dimensional vector. And the output layer is a scalar or one-dimensional vector. And when we think about this network, we can always think that the input to a layer is a vector and the output of a layer is also a vector. By contrast, CNNs arrange the neurons as rank 3 tensors, that is typically as rank 3 tensors, 3D arrays, and these tensors have a width, a height, and a depth. In the visualization to the right, we can look at one such tensor. And the whole network is seen in the way that you see that the red box here is the input tensor, and then it's passed through the first convolutional layer that is drawn as an arrow here, and then you get a tensor that is a bit smaller but deeper, and then you get this tensor here. And so here we see the label as width and height and depth, and what we use is width and height to denote the spatial resolution of the tensor, and depth denotes the number of channels. So in this visualization here, there would be 5 different channels. And each channel we can think of as a grayscale image that has width, and height, Let's look at this example network here, where you see to the left the input image that is passed through multiple convolutional layers, and at the end you see the classifier that predicts different classes. And the probability of a particular class is given by this green bar. So the larger the green bar, the higher the probability the network thinks a certain class has. And then these output classes are ordered according to probability. So you always see the 5 most probable classes. In the middle, we see a visualization of the activation maps. So when an image is passed into the network, then these activation maps show how does the network react to the image, what is the data in all these intermediate tensors that are processed by the network. So these activation maps are probably sorted from top down. So these are the different channels. And then as you go from left to right, these will be the different layers of the network. Here's also a more detailed explanation of the network architecture. So the first column is the output of a convolutional layer that we will discuss. Then the second column is the output of a ReLU layer, a nonlinear layer, and so on. And then you also see this red these are example of pooling layers. And convolutional layers and pooling layers will be discussed in this lecture. We would like to establish a link to the traditional convolution that you study in some form of engineering or mathematics course. Convolution takes two functions f and g as input and produces a function h of x as output. The notation is h of x equals f of x, and then you have this convolution symbol here, g of x, and that equals to the integral from minus infinity to plus infinity of f of u g x minus u du. So one thing to note here is that for each output value of the function h, so for each possible output value x, you actually have to compute this integral. And the integral takes one of the functions, so the first function f, but it's interchangeable as we will see, takes one of the functions, then it takes the second function and it translates and flips the function, and then these two functions together we will compute an inner product. Note that in this formulation, g of x is flipped. And some people tend to use the term correlation to define a version of convolution where the filter is not getting flipped. And this is also used in PyTorch. So, but you cannot really rely on that. People use these terms sometimes interchangeably. So here are some fundamental properties of convolution. First, the order can be switched, so convolution is commutative. So f of x convolved with g of x is the same as g of x convolved with f of x. The order can also be changed, so it's associative. F convolved with the result of g convolved h is the same as first convolving f with g and then convolving with h. Also, the convolution of a function f with a sum is the same as convolving f with each of the terms and then computing the sum. So here we have a visualization of how convolution works. We are going to convolve the function f of x with this function g of x. And we consider g of x to be the filter. Now, what we're interested in is to compute the function for one particular output value. So what is the final result? Convolving f of x with g of x gives us this function h of x. And what we're visualizing is the computation of this one particular output value that corresponds to this x-axis location. How do we get it? For this, we'll look at this area here. First, we'll use this x-axis is labeled u here, and we'll take this function f of x and we copy it down here, and we'll call it f of u. Then we'll take this function g of x and we will position it exactly at this value that we're interested in computing, and we are flipping it. So we'll take it, copy it, and flip it. And this copying and flipping and translating is encoded by this g of x minus u. So then we compute a component-wise multiplication of the function f of u and g of x minus u. And so you can see when we're here, then this is going to be 0, 0, 0, 0. Nothing happens because the filter value is just too small. And then here maybe we start seeing the values increase. So the component-wise product between these two functions is visualized by this function here that is labeled f of u times g of x minus u. And then what we do is we integrate up this function. So this particular value here is the integral of this area that is shown in dark gray here. That is the integral of this function, that is the component-wise product of f of u and g of x minus u. Very often convolution is used to smooth a function. This is the typical example that is often given when explaining convolution. So here we show one such example. The function f of x is a function that has quite a bit of noise, so you see it's kind of going up and down quite a bit. And we are going to convolve this function f of x with this filter function g of x to obtain a smoother function h of x that is shown as a dashed line, and you can see it's a smoother version of f of x. Convolution can be described in the continuous form as well as the discrete form, and the discrete form is often more relevant for computer science. So let's look at this, how that works, at least more relevant for the implementation. Let's say it this way. So we have h of x, and now this notation says that this is more like this is like an array, so a discrete function is given maybe by an array of numbers, and x is the index into this array. So we have h of x equals f of x convolved with g of x, and then you see maybe these are conceptual areas of infinite size. That is case you sum up from minus infinity to plus infinity f of x times g x minus k. So this is a straightforward discretization of the continuous equation we had before. Now let's switch back to continuous and look at convolutions for functions of two variables, and the extension is fairly straightforward. You still have the same idea that you'll take the first function, you just copy it over, and then you take the second function and you translate it based on two variables now, u1 and u2. You can think of this as the x coordinate and y coordinate offset that is used to translate this function. And now we have a two-dimensional integral, so we'll integrate over the one axis u1 and the second axis u2, and we'll have a two-dimensional integral that gives us the area of the component-wise product between these two functions. And here, if you're interested, is the discrete form. Again, it's a completely straightforward discretization. There's a link to some convolution examples, and we already saw blurring in 1D, so why not look at one example that is more like edge detection in 2D. And here the filter is this 3x3 discrete function. And what does this filter do? It will kind of measure discrepancies between the current pixel value and the 8 neighbors. So if we are at the constant region, we would expect the filter response to be almost 0, because we would expect that 8 times looking at the current pixel is going to be the same as subtracting out each of the neighbors. But if there's a discrepancy, some form of edge, then the filter will have a higher response. So convolving this filter with a given grayscale image will function as some form of edge detector. So here's a result. You see there's a building here, And this is the result of the convolution of this building grayscale image with the filter I showed before. What you can notice is that this output highlights edges. So for example, this is an edge on the roof line here, and this edge is clearly visible as in the output of the convolution. We're going to look at the numerical example for 2D convolution. So this is just so the information is on the slides. We're only going to look at the example visually. We have an input image I that is convolved with this filter K, and as output we obtain this, let's call it also image I convolved with K. First thing you notice is that the image I has a different resolution than the image I convolved with K than the output image. In particular, the input image has size 7 × 7 and the output image only has size 5 × 5. What we are doing to compute a particular output value is we're going to take this filter K here and we're going to place it over a particular pixel. And what I like to do conceptually is typically I think of, and this mainly works when the filter is symmetric, I think of the center pixel of the filter, and I'm gonna place it conceptually over some pixel in the input image I. So I'm gonna align the 1 with the 3, and then this 0 will align with the 4, and this 5 will align with the 1. So we think of this filter K is now being moved over, so this red rectangle is being moved over exactly over this blue rectangle, which is a square. All right. So now, in order to compute an output value, I will take the product between the values that are overlaid and then sum up each of these individual products. So 4 is kind of registered with 0, so we compute 4 times 0 plus 1 times 0 plus 1 times 2 plus 1 times 3, 3 times 1, and so on and so forth. And the final result is going to be 13. So the final result is shown here in this green pixel that gives us 13. The x's here just denote that I was too lazy to compute all the output values. You could check another value, 20, that should be obtained by now aligning this red box with a square that is shifted by 1 pixels to the right, so it should be overlaid here. And then again we compute all the we compute the multiplication of each value with whatever in the image with a value here in the filter, and then we sum up. So why is the output different? Well, if we would like to position this filter K in this input image I, it will only fully fit in fewer locations as there are pixels. So for example, we cannot align this value 1 with this value 0 because then these values at the top would go out of bounds, so to say, and couldn't be aligned with anything. So what we're looking here is convolution, where the filter K needs to be fully inside this image I. That means is that the output here, which is second row, third column, is obtained by aligning this one here, and so it's basically by aligning the center of the filter with the third row and fourth column. So there's a shift of 1 in rows and columns. So I'm thinking of putting the filter over element 3, 4 here. In the output corresponds to element 2, 3. So 1 row less, 1 column less. One parameter to configure the convolution is stride. We can subsample the output before or after. So conceptually after you do the convolution, but computationally, of course, you just compute the convolution values only for specific locations that are fewer than all the locations. So we use the term stride to denote the subsampling amount. If stride is 1, that is the default, no subsampling occurs, and you move the filter 1 pixel each time. If stride is 2, then you skip every second pixel and move the filter 2 pixels each time. So you could think of stride telling you when you computed one of these inner products between the filter and the image at one particular location, how many pixels to the right or to the bottom when you're finished with a row should I move the filter. So in the visualization here, you see that the orange values denote the locations where the top left of the filter can be positioned. So now we want to align the top left of the filter with values in the input image, and you see that there are only 3 by 3 such pixel locations where the filter can be positioned. Therefore, the output of this strided convolution is 3 by 3. Again, you note some form of an imbalance, that the filter locations here are only on the more on the top and to the left. You could also think about it conceptually as visualizing the pixels where the center of the filter is located. Then, for example, this 1 and this 1 and this 2 would be colored orange, and then this visualization would be more symmetric. Now, this boundary problem is not really great because the images tend to shrink when convolution is used. To combat this shrinking, one parameter on how to configure convolution is padding. And padding means that we artificially enlarge the input image, and we create a boundary that has a spatial extent. So if the boundary has, let's say, padding size 1, that means we add 1 column to the left and to the right, and 1 row to the bottom and the top of the image. So just going to this visualization, this is a padding of size 1, padding with value 1. So you see basically a ring of zeros that are in orange. These are the new values that are added to the input image I through the padding operation. And you can say that here all these new values are set to 0. However, we can ask, what values should we use for padding? Maybe 0 seems to be a sensible choice. That's actually very popular. That's the default choice. Other ideas exist. For example, you could copy the value from the nearest pixel. Let's go back to this example here. So copying the value from the nearest pixel, if you wanted to know what is the value here, this would be a 2, because 2 is the nearest value here. How about the corner? To fill in this corner value here, we would copy this 8 over here. So actually you notice that this 8 would be copied here, it would be copied over here, and it would be copied over here if we use this nearest neighbor padding idea. But there's also the idea to do this toroidal topology, to do this toroidal copying. You might know that from old video games, you go out to the left, you come in to the right. So let's look at an example here. We want to know what value should we fill in here. Then we go out here and come in here, so we end up here. So we would copy the 0 over here. Similarly, here we would copy the 1 from over here, And if we want to know what value to fill in here, it would be 5, because we would fill in the value 5 here from the bottom. And here we would fill in 3, copied from here from the top. How large should the padding region be? Typically, the padding region is proportional to the filter size, and you might want to ensure that the output image has the same size as the input image. For example, a 3 × 3 filter uses a padding size of 1. A 5 × 5 filter uses padding of 2, and a 7 × 7 filter uses a padding of 3. One way to visualize this conceptually is you can think of this old image or this input image that is shown in black, and now you take this filter and you want to take this central pixel of the filter and locate it over the top left pixel here. So you take the 1 and you move it over the 0, and then you see how many rows and columns are sticking out and require some padding. So if we move the 1 here, then we would see we need padding of 1. But if you imagine this to be a 7 × 7 filter, then there would be 3 rows on top of the center and 3 columns to the left of the center. And then this explains why you need a padding size of 3. All right, sorry here. So there's some 2 terms. Same padding means that you set the padding parameter in conjunction with the filter size such that input and output tensor have the same size. Valid padding basically means no padding. In valid padding, you only place the filter inside the input tensor image wherever it is allowed. So valid padding is the option that leads to a shrinking of the spatial resolution when convolution is applied. All right, let's look at this again. So here we have an input image I, and the input image I is shown in black, and it has resolution, spatial resolution 7 × 7, and after padding with a padding value of 1, it becomes a 9 × 9 image. And now, convolving this 9 × 9 image with this 3 × 3 filter K gives us output a 7 × 7 image, where in black you see the values that would be produced by valid padding, that means no padding, and then the orange values are the ones that are produced in addition because we padded the input image I with these orange zeros here. Let's again conceptually think about what happens. So now if we take this 0 and we place it over this, we take this center of the filter 1 here and we place it over the 3 here, what you see is that counting the position in the original image I without padding, we are in the 3rd row and 4th column of the original image, and now this green value here corresponds to exactly the same, which is the 3rd row and the 4th column of the output. This is what we want, so now things are nicely corresponding. So each value in the output tensor has a nice correspondence to the values in the input tensor. There's a direct kind of relationship that they are at the same spatial location. Another way to configure filters is to use dilation. Dilation creates filters with a structured sparsity pattern. And this can be used for a multi-resolution effect where you actually want to aggregate not only information that's very close by, but also information that is further away. So this is a filter that would use the setting dilation equals 2. And so only values at the orange axis could be set, and all the other values are 0. Of course, when implementing the convolution with such a sparse filter, you would not compute all the multiplication of zeros with other values. You would know the sparsity pattern, and you would only seek out to combine the orange values with whatever, with the image values at the corresponding locations. Now, this dilation can be very large, then you have a filter that is very large and very sparse. Next, we want to extend to convolutions on rank 3 tensors, for example, 2D RGB images. What you see here to the left is a red, green, blue image of resolution 32 times 32, and it has 3 channels, depth equals 3. To convolve an image with a filter, we now have multiple design choices to pick from. The one that we are using is to extend the filter to have multiple channels as well, and the filter will have exactly as many channels as the input tensor has channels. So the input tensor shown in orange has 3 channels, so now the filter itself also has 3 channels. It has a depth of 3. In a grayscale image, so the spatial resolution would be 5 times 5, and then extending it would give a 5 times 5 times 3 filter. So what we do then to convolve is we will place the filter again over a particular location, and then we will compute all the products between the values that are overlaid, and then we sum up all these values. Also very important, don't forget the bias. This is a big difference between convolution in traditional math and engineering and convolutions in convolutional neural networks. There's a bias term that will also be added to the result. So how many values do we need to define this convolution? We would need 5 times 5 times 3 equals 75 values, plus 1 for the bias term, so 76 values to go from this orange input tensor to this blue output tensor. You notice that the resolution here, the output resolution of 28 times 28, is indicative that valid padding or no padding was used. Therefore, the input tensor shrank in spatial resolution by from 32 times 32 to 28 times 28. Let's also think about how many values would I have to use if I wanted to compute the fully connected layer that has that many inputs and that many outputs. So here you would need to have 3 times 32 times 32 plus 1 weights for each of these output pixels. So this would be a much, much larger number, significantly larger. And so one thing that we can observe here is that using convolutions leads to layers that have significantly fewer parameters than fully connected layers. Let's also think of other design choices. Why extend the depth of the filter? Why not simply take a 5 times 5 filter and use it to convolve the first layer, which gives one output activation map, then convolve the second layer, second channel, to give another activation map, and then convolve the third channel to give a third activation map. So the one possible problem could be that the filter has a specific meaning and it works especially together with one particular channel, it's not likely that the same filter can extract meaningful information out of all the channels. Because we could imagine that the channels encode completely different things in the network, and so it's not likely that the same filter can extract meaningful information. However, I would consider it a valid design choice nevertheless. The other problem, though, is that this would create possibly a very large number of output activation maps. Another idea then is to use maybe one filter for the first channel to create an output activation map, and a second filter for the next channel to create another output activation map, and a third filter for the third channel to create another output activation map. So now we would have almost, except for the biases, almost the same number of parameters than the most dominant filter design, but we would have more activation maps as output. Actually, we would just gain a lot more flexibility, but it would come at the cost, again, of having a lot more output activation maps. So while I still think that this filter design makes a lot of sense, it doesn't seem to be used a lot. Or if it's used at all, I don't know. So there are ways to implement that, though. At least there's a whole range. So a filter, for example, could be applied only to a subset of input channels. So this is kind of saying that, well, maybe not one filter for each input channel, but let's define a bit deeper filter that is applied to only a subset. So for example, if we have an input tensor that has 100 channels, then we could have a filter of depth 50 that will be convolved with the first 50 channels, and another filter of depth 50 that would be convolved with the next 50 input channels. In order to obtain more output activation maps, more channels in the output tensor, we'll just use multiple filters. Let's just think of our example before, where we had a filter of size 5 times 5 in the spatial resolution times 3 times depth 3. This would give us one blue activation map. And then if we want to get 6 output activation maps, 6 output channels, we would need 6 different filters. They could all be the same size. So let's say 6 times 5 times 5 times 3, and then we would also need 6 bias values. So let's just look at this. So the number of channels in the output tensor is equal to the number of convolutional filters used in the convolutional layer. Also, after a convolutional layer, we typically want to use a nonlinear activation function or a nonlinear layer on the output tensor of the convolutional layer. The reason is that just stacking convolutional layers on top of each other just gives conceptually something that can be combined together to have another convolutional layer. So just doing lots of convolutional layers in sequence is the same as doing a different type of convolution. And inserting a nonlinear function between two convolutional layers creates something different than a convolution as a final result, something that's a lot more powerful, a lot more flexible, has a lot more expressiveness. So we want to interleave convolutional layers with nonlinear layers, such as the ReLU, and stack them on top of each other. So here an input 32 times 32 times 3 tensor is processed by a convolutional and a ReLU layer to yield this 28 times 28 times 6 tensor, which then again is processed by another convolutional and ReLU layer to yield this 10 times 20, this 24 times 24 times 10 tensor, and so on and so forth. Maybe looking at one particular convolutional layer, to go from here to here, we know that the filter that is being used has to have a depth of 6, because there are 6 channels in the input tensor here. And how many filters do we have? We can also read that here we need as many filters as we have output channels in the output tensor. So this number 10 and this number 6 we can read off from this figure here. The spatial resolution of the filters we do not know, so this is just an example, 5 times 5 here, but this might also have been something else. But maybe what is a hint on the filter size? So the hint on the filter size is how much did actually the resolution decrease here. Since the resolution decreased from 28 times 28 to 24 by 24, now assuming that valid padding was used, this makes sense that that we have 5 times 5 filters. So in the PyTorch documentation, you will see that we have a lot of different parameters that you would need to look up. And the one thing that I wanted to highlight is that the convolutional layer needs to take a batch of rank 3 tensors as input, and this batch of rank 3 tensors is organized as a rank 4 tensor. So these are the 4 axes of the rank 4 tensor, the number of samples, so how many rank 3 tensors do we have, the spatial resolution, width and height, and the number of input channels. The output rank 4 tensor needs to have the same number of samples as the input tensor, but the spatial resolution and the number of output channels can be different for each of the output rank 3 tensors. If you read the PyTorch documentation, you will note that PyTorch uses the channel first convention, so they will write the channel axis before the spatial width and height axis, so this C will be written in front of the W. You can have different types of convolution. There's not only 2D convolution, but also 1D convolution and 3D convolution. 3D convolution makes sense to process videos or volumes. Example volumes would be medical scans or output of simulation data, density data inside a room, or some other, maybe a volume describing some smoke or a cloud. So what I wanted to note here is that the filters then have 3 values to describe the spatial extent. So let's say this is x, y, z extent of the filter. And then we also have the number of input channels of the input tensor. So for 3D convolution, if we process, we would have an input tensor that has rank 4, output tensor of rank 4, and then if you do batch processing again, we would process rank 5 tensors as input, giving rank 5 tensor as output. One interesting convolution is the one-by-one convolution. The one-by-one convolution, to someone knowing the traditional convolution, makes no sense at all. So what happens here is that a one-by-one convolution will be applied to each pixel in the input tensor separately. So we have an input tensor here of spatial resolution 56 times 56, and we have 64 channels. And a 1-by-1 convolution would take 1 pixel here, and it would extract all the values across the depth. It would extract 64 values for this pixel, and then it would perform convolution with a 1-by-1 by 64 filter. So each filter would have size 1-by-1 times 64. And what this does is, in fact, it's running a separate, fully connected neural network on each pixel. So you could just imagine someone adds a fully connected neural network that operates on each pixel separately. And also, if you think about what is the expressive power of such a 1-by-1 convolution, then you would notice that it can actually encode something like singular value decomposition or PCA. And the idea is that you could think of having maybe a first principal component, and now you want to project this tensor using maybe principal component analysis, then the first output channel would correspond to the first principal component, the second output channel to the second principal component, and so on. Highlighting this is just to give some intuition that the 1-by-1 convolution typically is used to give some form of dimensionality reduction. This assumes that you have some previous knowledge in SVD and PCA and to know, and dimensionality reduction to know what that means. It's some form of maybe compression to reduce the number of channels, but hopefully have a tensor that has the most important information preserved. Let's summarize the basic convolutional layer. We have an input tensor of size width times height times number of channels, and I use this subscript in to denote that this is the width, height, and number of channels of the input tensor. The hyperparameters are the number of filters k, the size of the filter f. So here we assume for simplicity that the spatial extent of the filter is symmetric, so the width and height of the filter is the same, and given by this one value f, the stride s, and the amount of zero padding p. We have an output tensor of size, width, height, number of channels. Again, subscript out denotes that this is for the output tensor, and we have the relationship that the number of channels of the output tensor equals the number of filters that are defined in this convolutional layer. The width and height can be computed by taking the input, the output of the output is taken by taking the width of the input minus filter size plus 2 times padding divided by s, the stride, plus 1. The number of parameters are for each filter are f times the number of input channels plus 1, and so the total number of parameters will then be f times c in plus 1 times k. Here are some example settings. Often the filter size f is small, so you will see a lot of usage of filters of size 3 by 3, 5 by 5, or 7 by 7. Using subsequent convolutions with small filters with small filter sizes f is generally more common than one convolution with a large f. In the beginning, popular, one of the first neural networks that was very popular, used a convolutional size of 11 by 11 in the beginning, in the first layer, but it was then rare for many years in the dominant networks. You don't see this convolution size anymore. So I would say that generally 3 by 3, 5 by 5, 7 by 7 are the dominant sizes. Same padding, or setting the padding as filter size minus 1 divided by 2 is a dominant choice. Then the number of channels, how many do we have? Typically, we process tensors that have powers of 2 number of channels. For example, 32, 64, up to 1024. It is not uncommon to see neural networks that have tensors with 512 or 1024 channels. And it is also not uncommon to see neural networks that process images where the resolution gets smaller and smaller and the number of channels grows to be larger and larger. So a standard 3 by 3 convolution, for example, you would use filter size 3, padding 1, stride 1. Downsampling is often combined with a 3 by 3 convolution, so you could see something like this should be f equals 3, peak padding is 1, but stride is 2. This is like a combination of downsampling and filtering. Of course, the non-symmetric treatment of width and height is possible. There might be some restrictions in the particular programming interface you use, but you can imagine everything can be changed, right? You could have arbitrary sizes of filters, arbitrary sparsity patterns. You could have different stride in the x and y direction. You could have completely crazy padding that is different for left, right, top, and bottom, and so on and so forth. So some of these things can be done with PyTorch. Now, of course, some choices are more common than others. So for example, having filter sizes that would be 1 times k or k times 1 is something you will see quite a lot. So you could say, for example, that a filter of size 1 by 7 or 7 by 1 would specifically look for horizontal or vertical features. Also, by going back to linear algebra and what you might or might not have learned about matrix factorization, the idea might be to take larger filters and factor them into these anisotropic filters that are basically vectors, and then maybe say, can we achieve a convolution of a large k by k filter by having 2 convolutions with a 1 by k and a k by 1 filter. So here are some links to websites or visualizations that I like. At this website, you see an animated visualization of convolution. So you see how here a 5 by 5 input image is convolved by a 3 by 3 filter, and using valid padding, you get a 3 by 3 output image. Going down further, so there are many nice visualizations. You could see how an input tensor of size 5 by 5 spatial resolution with depth 3, so 3 different channels, is convolved. So the input, the filter here is of size 3 by 3 by 3, and the convolution operation conceptually uses one filter to convolve the first channel, the second filter to convolve the second channel, and the third filter to convolve the third input channel. This then yields, again using valid padding, 3 different 3 by 3 images that are then added up together, and then one constant offset is added to each of these values, and then as output you get the overall result of convolving this 5 by 5 by 3 input tensor with a 3 by 3 by 3 filter. So more information here. So here's another website with some visualizations that I found quite interesting. So you can see, for example, visualization using padding and strides. One term to know is the idea of the receptive field. How I would define it is that the receptive field of a neuron or particular value in a tensor is the area of the original input tensor that can influence the value of the neuron. So you might look at some value in some intermediate tensor in the network, and you ask what input values can actually influence this particular value. And what you will notice is that if the receptive field is small, only a small area of the input can actually influence this value, then the computation will be very local, and you can only basically consider local information around that particular pixel to influence the value. If the receptive field is very large, then a lot or maybe even all input values can contribute. So the receptive field can also be basically discussed with respect to any layer, not only the input. Now let's discuss pooling. So in this example, we'll just look at max pooling. And it's so simple that it could be completely understood from this example. Let's say we have a 4 by 4 input image, and we use max pooling with a 2 by 2 filter and stride 2. So what we do is we basically look at this 2 by 2 area and we compute the maximum. So the maximum is 6. So we copy this 6 over here. So this red 6 corresponds to the maximum of this 2 by 2 area. Then this 8 is the maximum of this 2 by 2 green area, and this blue 4 is the maximum of this 2 by 2 blue area. This is a simple downsampling operation where the lower resolution image always aggregates a 2 by 2 block of the high resolution image by taking the maximum. If you have an input tensor that has many different channels, then the pooling operation is simply computed per channel. So let's say we have a pooling operation that does a downsampling by a factor of 2. That means the spatial resolution from 224 times 224 will be reduced to 112 times 112. Then this pooling operation proceeds channel-wise such that the number of input channels is the same as the number of output channels. Different pooling operations exist. There is max pooling, average pooling are two popular ones, and then there are some crazier ones like max unpooling, fractional max unpooling, and so on. So you can look at the documentation. This pooling also has parameters, stride, padding, dilation, to give you several options. Now this is basic, it's max, maybe it could be anything, basic pooling parameters. We take an input tensor of size w times height times depth, and there are two hyperparameters, filter size and stride, and then we produce a volume of size, again w times height times depth, where the depth of the input needs to be the same as the depth of the output, and there's a relationship between the spatial resolution that depends on the filter size and the stride. So it is not common to pad the input using zero padding, and this is a filter, so this is a layer in the network that has no parameters. So there are no learnable parameters here. So it's a fixed function of the input. The most common setting is to set the filter size to 2 by 2 and to have the stride to be 2. This is the max pooling showed before. You can have some crazier versions. Now, while these crazier versions might be used, maybe it's more to create some form of novelty effect, but the crazier versions are probably not dominant. Let's just build up a network. So a classical convolutional network architecture would repeat several blocks of convolutional layer, ReLU layer, pooling layer. And the pooling layer decreases the resolution. You could also have convolution, ReLU, and then pool. So, of course, many versions are possible. Then you flatten this tensor to a vector and repeat several blocks of fully connected layer ReLU, fully connected ReLU, and then there's a final fully connected layer. We can convert fully connected layers to convolutional layers and convolutional layers to fully connected layers. First, any convolutional layer can be converted to a fully connected layer. What you need to do is you simply create a weight matrix for the fully connected layer, and we can observe that this weight matrix would have a lot of zeros. Also, the parameters of the convolutional layer would be copied many different times. So this would not be explicitly encoded in the fully connected layer. There would be just a lot of copies of the different values. If you would like full functional equivalence, then this weight sharing would need to be encoded. That means that certain values inside the weight matrix are tied together to be the same. However, in a forward pass, at inference time, when the neural network is run on a particular input, that is not a problem. That is only something to consider at training time. Conversely, a fully connected layer can be converted to a convolutional layer. Particularly of interest is the conversion of a fully connected layer that is applied to a tensor that is flattened and then input to the fully connected layer. So what we do is we simply set the filter size equal to the size of the input volume. Let's just say we have an input volume of size 7 times 7 times 512, and then this input volume is flattened, inserted into a fully connected layer, and then we have 4096 outputs. What we do then is we kind of remove this flattening and the fully connected layer, and we replace it with a conv layer that has filter size 7, matching the spatial resolution, padding 0, stride 1, and there would be 4096 filters. Now, what is important to note here is that nothing changes when we do this replacement. However, the goal is to make the network more resolution independent. Let's just say that we have a network that is built that has a bunch of convolutional layers and at the end a few fully connected layers. So we'll imagine our network takes 224 times 224 RGB images input, then there are a bunch of conv layers, and eventually we end up with a 7 by 7 by 512 intermediate output tensor. And this is fed to a fully connected layer. If we then replace this fully connected layer with a convolutional layer, then what we can do is we can actually take input images that have a higher resolution. So in this example here, there would be also additional fully connected layers, but let's just think of this input image resolution going from 224 to 384. Now, having this larger input resolution, the convolutional layers that have been in the beginning, they don't struggle with this, they can easily adapt. So now the intermediate output will have an intermediate volume of size 12 by 12 rather than 7 by 7. And applying this convolutional filter to this 12 by 12 volume, this 12 by 12 tensor, will now give, instead of a single output, it will give an output of 6 by 6. So instead of having 1,000 class predictions for the input image, we will now have 6 by 6 by 1,000 class predictions. Then, if we really want to run this as a classification network, we somehow would have to aggregate these class predictions. But the idea here is simply, the general idea here is simply that by replacing fully connected layers with convolutional layers makes a network that was resolution dependent before resolution independent, and allows this network to work on a much broader range of images that have a different resolution. Having only convolutional layers is an important ingredient to make convolutional networks resolution independent. Let's look at this visualization of tensors inside the network again. As input, we obtain an image, we have an image, and the image is a red, green, blue image, so we can visualize it as red, green, blue color image here. This image will be fed to a conv layer, and the output of a conv layer will be of size 32 times 32 times 16, and what we see here is a visualization of the output tensor, where we visualize each channel, each activation map, as a separate grayscale image. So how many filters do we have? We have 1, 2, 3, 4, 5, 6, 7, 16 filters. So we have 16 output channels, 16 activation maps. And you can try to find a correspondence between this input image and these activation maps, and it kind of looks like some form of, everything looks a bit like an edge detector, but it's kind of hard to say what exactly it does semantically. After the conv layer, we have a ReLU layer, and the ReLU layer will set small values to 0, so you can think of it as kind of keeping the parts of the image that are important to the network, and you can also notice that the ReLU layer really sparsifies the input. So there will be large areas of black, and only certain regions in the image will respond. After that, there will be a pooling layer that reduces the spatial dimension from 32 times 32 to 16 by 16. You can also observe that the number of channels, as discussed, remains constant when applying the pooling layer. So we had 16 input channels and 16 output channels. Then there's another conv layer, and this time we have 20 different filters, so 20 different output channels, output activation maps. You can look at them again here. And then the sparser version that are output from the ReLU, again some pooling, and so on. You can also see that the weights are visualized and some of the gradients during the optimization are visualized. And this is something you can look a bit more on your own if you're interested. Later on, we will discuss multiple ways to visualize what a network is doing, and the summary might maybe be that it is quite difficult to visualize what the network is doing apart from the first layer. In the first layer, the filters have depth 3, so they themselves can somehow be visualized as color images. One problem, though, is that visualizing the filters as color images works well for filters that have a large size, so for example 11 by 11, as was used in the beginning. However, with more current networks using filters of a small size, such as 3 by 3 on the input image, then these filters are not terribly interesting, and it's very difficult to interpret what they do. From looking at some of the older networks, it kind of makes sense, and what the semantic interpretation might be is that a lot of these filters look at edges of different orientations, and especially they also look at color edges that are kind of contrasting colors. So this is kind of hard to see here. Maybe we'll see something like this later. So this is an attempt to visualize layers further down in the network, but this is something we'll delay to later in the course to see how that works in detail. All of these visualizations will have some advantages and disadvantages and are not straightforward. The one thing that is in some sense straightforward is the visualization of activation maps as grayscale images, where you can see what happens inside the network when a particular image is fed in. All right, this concludes this lecture.